So in this module we will be talking about some of the applications of computational electromagnetics, and in particular an interesting area of research called inverse imaging. Okay, we've all heard the word imaging, and usually we think of a camera taking photographs, but now the question is, can the same thing sort of be achieved using microwaves? Okay, that is what we will try to explore, and we'll see what are the advantages, disadvantages, and some of the challenges. Okay. So first of all, what is inverse imaging? Right. So you have looked at this course so far has been entirely about forward problems. When I say forward problem, what do I mean? That you are given the permittivity. Let's say you are also given the E incident. These two are given to you, and you have to find the radiated or scattered field. Right. This is what we did in integral equation methods, finite element method, and finite difference time domain method. Right. And we also know that you get like a matrix system of equations which has full rank, and therefore it has a unique solution. Okay. So there is also a uniqueness theorem which we have studied in the earlier modules, which tells us that there is a given certain conditions as a unique solution. Okay. From an engineering point of view, the more interesting problem is what is called the inverse problem. So what happens in the inverse problem? I am given the scattered field. So this is what is given to me. Okay. And the question is, what is permittivity as a function of space? Right. So there are at least three different kinds of examples where this is useful. For example, buried landmine detection. So let's say you have some ground over here, you have some landmine buried over here, and what you have is some kind of a sensor. So this can be thought of as like an antenna array. So they are sending fields everywhere, and what happens is when it hits this object, right, some of the fields will get scattered back, and this antenna, both transmitter and receiver, both are there. So what it is doing, it's you sort of take it over the ground and collect the scattered fields, and then you solve a mathematical problem, assuming you have not been blown up already, to get what is the permittivity as a function of space. Right. So this epsilon r as a function of space is very important. If I am able to get this in this domain, that means I have got an image of epsilon r, relative permittivity. Now typically these landmines are made out of different materials. Right? It could be a metal, it could be plastic explosive, whatever. It's different from the permittivity of mud. So it should show up as something different. Then I can say, okay, he looks like there is something unusual over here, take it out. Right? That is one application. Other application could be detecting, for example, what is called structural health. So structural health of what? Could be anything. It could be, for example, some bridge or cracks in concrete. That's what civil engineers use these kinds of applications for. Let's say I have some structure and I can't open it up, right? Let's say there's a load bearing wall. I can't open it up to see whether there's a crack in it or not. But if I can get epsilon r as a function of space, then I can see, oh, there is a crack running to it. So that information is somehow there in the scattered field, and I want to get it back, right? And one other very interesting problem is breast cancer detection. So I will talk a lot about this as we go forward. Okay, so how it's possible, etc., etc. Okay, so is the setup clear? What is meant by inverse imaging? Right, inverse because it's an inverse problem. Imaging because we want to get an image of permittivity, and its permittivity may be complex. Doesn't matter. I'll get a real part and I'll get a imaginary part. So that's what inverse imaging is. So as I said, we will talk more about breast cancer, right? So this is just some facts which we should all know. So there was a study done by AIIMS in India very recently, and they rated breast cancer as having the highest rate of both incidence and mortality amongst Indian women. Earlier it used to be cervical cancer, now it is breast cancer. And we have all heard amongst our extended families and friend circle, someone or the other has got it in recent times. And what is very alarming is that there's a ratio called mortality to incidence. So that means if 100 people got this disease, how many died? So that number in rural areas is very large, 66. In urban areas it's much less, it's 8. right? There's a huge difference between rural India and urban India. And so the study also identified one of the main reasons was a lack of diagnostic aids. There is not enough screening that is happening, and by the time you detect it, many times it's too late, right? And why is there such a big difference between rural and urban India is simply access and affordability of some kind of diagnostic tool that can catch this early on. Okay, so this is sort of facts information, right? So let's look at how things are done currently. So one is of course MRI. We all have heard of the wonders of MRI technology, right? So it produces very accurate and sort of precise images of any part of the human body, not just breast tissue, but any, right? And that's one way. And the other way is shown on the right is what is called X-ray, which is also something you are all familiar with, right? Now, both of these methods, if you can see, so let's talk about MRI. Of course, it's expensive, not everyone can afford it, and it takes a lot of time, right? It's not just the time in the machine, but the preparation time for the patient, everything, getting it done and all, it's time consuming. And it's again something that is limited to urban centers where such expensive equipment is there. You can't have, think of having an MRI machine in every village. You don't even have the electricity supply to give a sustained operation of this device, right? So that's the problem with MRI. What's the problem with X-ray? Right? So X-ray is cheap. I mean, it's not that expensive. You can imagine having it in many places in the country. But the problem is, it causes radiation damage. So that's why doctors will say don't get too many X-rays done, in a given period of time, because the more you expose yourself to X-rays, the more that genetic mutation can happen. And although you're trying to detect cancer, you may end up getting cancer because of getting very frequent X-rays. So here is the question that can microwave help us in any way, right? So of course we need methods that they have to be safe, means no radiation damage, and if this big divide between rural India and urban India has to be bridged, then it has to be inexpensive, quick. Of course, non-invasive is something that everyone wants, right? I don't want to have a biopsy done every time I want to check for this, right? So non-invasive is a no-brainer. We want non-invasive, right? So the claim is that microwave or radio frequency RF technology, it has the potential for at least these two reasons. The first reason is that RF waves can penetrate human tissues and not cause permanent damage. So it's been at least 2-3 decades since we've been using cell phones. So it's not, if it were really, really unsafe, no one would be carrying cell phones in their pockets anymore. There are reported cases of people who have spent a lot of time close to base stations where the radiated power is much higher, and that has known to cause some health effects. That's another thing. But when I'm talking about the radiation levels from a phone, it's okay. It's not something very dangerous for us. So we know that they don't cause damage, right? So that's safe, the safe part of it. And the other part is that the components are very cheap. Why? Because, well, telecom. How much do you get an ordinary mobile phone for these days? The most ordinary phone you can get for 1,000-2,000 rupees. That tells you that the RF components, the transmitter, receiver and the RF circuitry inside is cheap. Otherwise, how could you get it at that price? Wi-Fi, every place we go to has Wi-Fi, right? And Wi-Fi works at what frequency? 2.4 gigahertz, right? So in this range, 1 to 10 gigahertz, you can get off-the-shelf components that are inexpensive, right? You don't have to design it, you can just buy it.
So what is the frequency range for imaging applications?
Good question. So what is the frequency range for imaging applications? So as I mentioned over here, we'll keep it roughly in the 1 to 10 gigahertz range, okay? So as you go to, well, we'll come to terahertz. Terahertz has other problems. It's to make a source that can generate terahertz is itself a challenging problem. So terahertz sources are themselves expensive. So one of your main goals was to keep it low cost. You don't want to defeat that by having a very expensive source. Your source is expensive, your detector is expensive, all of those things. Then at some point you will be like, oh, may as well do MRI, right? It's true that terahertz will give you better resolution, okay? And in fact, there are these airport security that the US has where they have a terahertz scanner, full body scanner, which shows you the presence of various objects, right? But those are very expensive equipment.
But for this terahertz has less penetrating ability,
right? Right. So terahertz of course has much less penetration depth. So microwave frequencies in this 1 to 10 gigahertz, we can hope that I can get a through and through picture of the body, and components are cheap. Okay. I don't want to go too low, because as I go to lower frequencies, what happens to the wavelength? Wavelength increases. So, I will get an image, but it will be very low resolution, right. The imaging resolution is it depends directly on the wavelength, right. Right. So, what is the sort of underlying physics that tells us whether or not we can image? So, everyone has seen this experiment in school, right. You have a prism, send light through it, and light gets bent, right. Now, the precise reason why light gets bent is because all the colors have different refractive indices, okay. That is the more detailed explanation. But what you can see is, why did this beam of light get bent in the first place? Because it encountered a different medium, different refractive index, right. That is what caused the wave to scatter, or in this case we will say refract. Right. Now, the same principle I can apply to microwave radiation, right. So, this is an example, this is a sort of cooked up example of a cross section of, let us say, breast tissue, which is given by light blue, and it has various components. Okay. So, those components, these are synthetically generated, but they could correspond to something, some fat tissue, some cancerous tissue. The light blue could be, for example, blood, all of these things. So, what happens is, when I send a wave through this medium, every time it encounters different refractive index or different permittivity, that wave has to undergo some kind of scattering. We have seen that. Now, we will collect back the scattered field, process it, and try to get an image. That is the idea. Okay. So, more precisely, it is known, so biologists have done this, that they have extracted cancerous tissue and they have extracted healthy tissue, and they have studied the microwave properties. So, they have studied the permittivity of these tissues. So, of course, cancerous tissue has different permittivity from healthy tissue. That was the first conclusion, right. As a result of which, it scatters the electromagnetic field differently, and that information somehow gets then encoded into the scattered field. So, you can imagine, in this case, I am sending some incident wave over here. If I have this blob over here, if this blob were not there, what would happen to the wave from here? It would just go straight through and through. But now, because this blob is here, some wave gets reflected back, right. So, this information indirectly is being encoded into the scattered field. So, the information is there, somehow we have to pull it out. Okay. Reflection will occur from healthy tissue also. Correct, right. So, he is right that reflection will happen anytime there is a change in refractive index, right. So, we will talk about how we will distinguish healthy and cancerous tissue. This sort of brings us to the setup for breast cancer detection. Okay. So, let us go over it step by step. Okay. So, this is sort of step 1. So, here I have this capital D over here is showing a domain of investigation. Okay. This could be cross section of your head, cross section of breast, or could be a tree trunk, could be anything. Okay. So, I am saying anything inside D is unknown. I want to determine what is the permittivity. So, what do I do in the ideal scenario? I surround this object by a bunch of transmitters and a bunch of receivers. So, each of these things can act as both as a transmitter and receiver. So, what I do is I send an incident wave from here. This will get scattered and collected by everyone, all of these guys, right. So, I have got one incident field, so many reflected or scattered fields. Then I switch it off and turn the next guy on. Okay. So, I will turn this guy off, turn this guy on, and repeat the same experiment. So, because the object need not be symmetric rotationally, I will get different information when I am seeing it from different angles. So, all of this information is stored, and now the physical experiment is over. There is nothing more I have to do. Data collection is all I need to do, okay, because it is non-invasive. I am not going and cutting or prodding or anything like that. Okay. And step 2 is where the real challenge is, right. So, I have to use these fields that I have collected and solve a mathematical problem. This mathematical problem is what is called an inverse problem, to get permittivity as a function of space, right. So, I want permittivity as a function of space. Now, as was mentioned, it can happen that healthy tissue will also scatter waves, cancerous tissue will also scatter waves. So, after having done all of this, what do I do? So, that actually brings us to step 3, the diagnosis part. So, biology and medicine, people in biology and medicine, they have already done the hard work. They have calculated permittivity for healthy tissue, unhealthy tissue, blood, fat, cancer, all of this thing is tabulated. So, once I have got my this epsilon as a function of space, I just look up each pixel. What is the value of epsilon? What is the nearest fit? Is it fat? Is it cancer? What is it? Right. So, that is how I can do a diagnosis of whether or not there is cancer. Can you repeat this experiment using backscatter field only? That means you just want to use one transmitter and one receiver.
No, instead of this circular arrangement, can I use this both transmitter and receiver in single side?
That's what. So, you are saying that I keep this transmitter on, none of the other receivers are there, and I just collect this field.
Yes.
Yeah, you can do that. Yeah, okay. So, maybe I'll turn it around to you. So, supposing I were doing breast cancer detection there. So, I mean, what I am showing you is actually a top view of what the device will look like. So, the patient lies down, okay, and there is a like a cylindrical chamber into which the patient is slightly lowered. So, patient is surrounded on all sides by transmitters, receivers, and you collect the field over here. Now, just thinking intuitively, if you wanted to solve this problem, and would you rather have so many receivers, or would you have, like the suggestion, only one transmitter and receiver? So, one transmitter sends and you collect back what is coming to you. Which is better? Everything need not scatter back. So, if you have the luxury, it is better to put transmitters everywhere, I mean receivers everywhere, so that you can collect all of the information that does not come back to the transmitter. I mean, okay, the dimensionality of the problem has not yet been set. Right now, this looks like a 2D problem, but right, I mean, it could be a 3D problem. So, I could have multiple layers of antennas, receivers and transmitters. So, then I have to solve a 3D inverse problem. But the way I have shown it for illustration, it looks like a 2D problem. It need not be. Okay. Now, so this is for breast cancer. Now, for something like landmine detection, there obviously I cannot have receivers under the ground. So, what can I do over there? As an engineer, what you know that you are losing information by not having receivers everywhere. So, what would you do? So, one answer is that you have no choice, you have to live with backscattered field. Is there a better way of doing it? Many antennas, right? So, if I have this is the ground and this is my device over here. So, let us say I have one transmitter over here. What prevents me from putting, so let's not call this a transmitter. So, let's call this the transmitter. So, let's call this a transmitter. What prevents me from putting more receivers over here? Nothing, right? So, this guy sends a wave and okay, it also collects back the backscattered field, but I mean if there is for example a slightly angled object over here, so this field will also go back to these points. More information is always better, right? So, if I were doing landmine detection, I would do this. So, it is a half space, right? I have access only to half the space. So, I should put as many transmitters and receivers as is possible given size, weight and all of these things. Okay. Can you think of an example where you do not even have that luxury? It is a very, very important and well known example. An example where like here, so we started with example 1, breast cancer detection, I could surround the object, very good. Then we came to example 2 where I could not surround the object, but still I could put more receivers. Airplane, right? Little bit more general than airplane is? RCS, no. Yeah, well, okay, RCS, but application wise, military and general space-based remote sensing. I mean, every country launches these remote sensing satellites to sense the earth, right? So, there you have the earth like this and you have one your satellite is over here, right? It is sending a radar wave. So, I am not talking about a passive satellite which just takes photographs, I am talking about a radar satellite. So, it has a radar, it sends a pulse, right? Here it sends a pulse. Of course, the wave is going to get reflected back in all directions depending on what is on the ground, but it is a radar in space. So, I absolutely do not have this luxury of having a swarm of radar satellites at the same point in space and time to collect. So, here I have access only to backscatter information. So, this is in some sense problem 3 is the most challenging problem, because I have very little information, yet I want to try to map the whole earth. Okay. So, the basic principle is the more you limit yourself, the harder you make your problem. So, before designing something, try to maximize how much information I can get in a given scenario. So, for example, cracks in a wall, right? If it were a column, then I have the luxury of surrounding, but if I have a huge wall, then it's like problem 2. Then I cannot go around, around it. So, then I will have an array of transmitters, receivers in the same plane, right? So, it's up to you as an engineer how you want to do it. Fine. Okay, let's just write it over here. This is remote sensing, and this remote sensing could be from space. It could be via a airborne radar as well, which is more common in the case of military application. You mount the radar on a aircraft.